Okay, let's apply our knowledge that we have and assign the oxidation numbers to certain of these species. H2S, okay, first of all, since this right here is a non-metal, hydrogen here should be a +1. So that means sulfur would be a -2, right? And it goes through the calculations here. Now, here you have SO3 -2. Oxygen is a -2, so times 3 is a -6. But then you've got this, it's still -2 here, so that means that the sulfur should be a +4. Okay, -2 equals 3 times -2 plus 1x. So x has to be 4. Na2SO4. Here, each of these is going to be a +1, right? Oxygen here is a -2, so there's 4 of them, so that's a -8. -8 plus 2 is -6. So that means sulfur has to be a +6 to balance the negative ions there. Okay, and this walks you through that whole process. So, now, using these oxidation number concept, you can have these redox reactions, which one or more elements undergoes a change in oxidation number. And remember, oxidation is an increase of oxidation number, reduction is a decrease in oxidation number. Combustion reactions, we talked about those already. The reductant, also called the fuel, is the oxidant, often but not necessarily the molecular oxygen, reacts with it to produce steady amounts of heat, often light in the form of flame. Solid fuel reaction. Here we've got something that's not a carbon material, but it's aluminum. Aluminum plus ammonium chlorate gives you aluminum oxide and generates quite a bit of heat in the process, and generates, instead of oxygen and water, it generates nitrogen in water as it is doing that. Okay. Here's another combination reaction where you have iron plus oxygen in this case, giving you iron oxide. And this is a simple combination reaction, 2 becoming 1. Decomposition, one compound is broken down. Okay, here you have mercuric oxide breaking down into mercury and oxygen gas. Replacement reactions, we talked about these. Here what you have is where you are replacing the anion here, and so it becomes XS plus XZ plus Y. Or here where you are replacing the cation portion, so X becomes the free element, and this ends up being AY. This is single displacement example. Here you have copper plus 2 silver nitrate forming copper nitrate plus aluminum. I'm sorry, silver is a solid. Silver is a silver nitrate. So you balance these by half reactions. Redox reactions take place and often involve water, hydronium ions, and hydroxide ions as the reactants. Although these species are not oxidized or reduced, they do participate in the chemical reaction in other ways. These reactions are difficult to balance by inspection. Okay, a useful method to approach these balances is the half reaction method. Write the 2 individual half reactions, the oxidation and the reduction. Balance all elements except oxygen and hydrogen. Then balance the oxygen atoms by adding water molecules. Balance the hydrogen atoms by adding hydrogen ions. Then balance the charges by adding electrons. Okay, those are the simple steps right there. If necessary, multiply each half reaction's coefficient by the smallest possible integers to yield equal numbers of electrons. Okay, then add the balanced half reactions together, simplified by removing the species that appear on both sides of the equation. For reactions occurring in basic media, there'll be excess hydroxide ions carrying out these steps, right? And then add hydroxide ions to both sides of the equation in numbers equal to the H plus ions. On the side of the equation containing both H and OH ions, combine these to form water, and simplify the equation by removing any redundant water molecules. Finally, check to see that the number of atoms and the total charge are balanced. So these are the 9 steps involved, and let's do an example. So here you have Cr2O7 plus Fe plus 2 going to Cr3 plus Fe3 plus. So the 2 half reactions, that's step 1. Here you have Fe2 plus, here you have Fe3 plus. Here you have Cr2O7 with a 2 minus, and you have a Cr3 plus here. Now, the first thing is to balance all the elements except hydrogen and oxygen. This one right here is already balanced. You have 1 here and 1 here. Now you have to have 2. You have 2 here, so you have to have a 2 in front here. Okay, so now these are both balanced in terms of the number of atoms on each side. You have to balance the oxygen atoms by adding water molecules. The iron half reaction does not contain oxygen. The chromium half reaction contains 7 here, and it contains none on this side. So you need 7 water molecules over here. So this will be Fe2 plus going to Fe3 plus, Cr2O7 2 minus going to 2 Cr3 plus plus 7 H2O. Balance the hydrogen atoms by adding hydrogen ions. Iron, this is already taken care of here. This shows with 7 here, okay, you must have 14 H plus here. So we're through step 4. Balance the charge by adding electrons. The iron half reaction shows plus 3 on the left side and plus 2 on the, plus 2 on the left side, plus 3 on the right side. Adding 1 electron to the right side brings this to 3 plus 1 minus, and the charge balance is achieved. Okay, so you're adding electrons to the one side of the equation. Okay, right over here. A chromium half reaction shows a total charge of 1 times 2 minus, okay, 14 times 1 plus, so 12 plus on the left-hand side of the equation, right? 14, 2 plus. On the right-hand side, you've got 2 times 3, that's plus 6, okay? Adding 6 electrons to the left side brings that the total side reaction is 12 plus equals 6 plus, and the balance is, and you've achieved your balance here, okay? Multiplying the 2 half reactions, so the number of electrons in one equals the number of the other, to be consistent, so you have 6 Fe2 plus, 6 Fe3 plus to give you 6 electrons here, which balances with the ones here, right? So when you combine these will cancel out. Now, so you're adding the balanced half equations and canceling the species that are common, right? So only the 6 electrons are redundant. Removing them on each side yields a simplified balanced equation. 6 iron plus 2, 1 chromate ion, 14 hydrogen ion. So a final check for the balance shows that all of them, in terms of charge and everything, are balanced. You've got plus 2 here times 6, 2 minus here, 14 here. So this is 12 here. This is 14 plus these 12, and a 2 minus here. Here you've got 3 plus and times 6, and 2 times 3 is 6 here. So this is 18 plus 6 for 14. Here you have 12 plus 14 minus 2, giving you 24 on this side as well. So that ends that section. Going on to ion exchange reactions, this takes place when either a solid precipitate, a gas, or water is formed. Okay, so you have something, interaction of one ion with another one, where something is removed from the solution, from the ionic equation. So many chemical reactions take place in aqueous medium. When ions are involved, the chemical equations may be written at various levels of detail. This molecular equation is calcium chloride in water, 2 silver nitrate in water, calcium nitrate again in water, and you have a precipitate forming of silver chloride. So molecular equations don't explicitly represent the ionic species that are present. If you broke it down into the different constituents here, it would be like this in this form right here. So you'd have 3 separate ones, and since this doesn't dissolve in water in any extent, it's just written as the AgCl with an S. Ionic compounds dissolved in water are more realistically represented as dissociated ions, and so they would that complete equation would then be represented as this right here. The net ionic equation is only removes those that are identical on both sides of the equation, such as the calcium and the nitrate. These ions are called spectator ions. Presence is required to maintain charge neutrality, but they're neither chemically nor physically changed by the process. Elimination of spectator ions results in a net ionic equation here. A precipitation reaction is one in which dissolved substances react to form one or more solid products, also known as a double displacement, double replacement, or metathesis reaction. Many reactions of this kind involve the exchange of ions between ionic compounds and aqueous solutions, and precipitation reactions are common in nature and in industry. What causes something to precipitate? Well, let's talk about solubility. Solubility is the maximum concentration of a substance that can be achieved under specified conditions. If substances have a large solubility, they're said to be soluble. That which is not will actually precipitate out of solution. Low solubility means that they are insoluble and will readily precipitate from that solution. And this is something you should write down in terms of what are soluble, and then the insoluble exceptions. Insoluble compounds containing these, soluble exceptions to these, right? So the group 1 metal cations and ammonium ion are usually soluble. Halide ions, acetate, bicarbonate, nitrate, chloride ions, and the sulfate ion. The sulfates of these particular ones are not soluble. The halides of these are not soluble. You'll notice that they're mostly silver, mercury, and lead. Insoluble ones are the carbonate, chromate, phosphate, and sulfide ions, and the hydroxide ions, except when the hydroxides of a group 1 metal cations and barium, the only one in the group 2. Compounds of these ions with group 1 metal cations and ammonium ion. So a molecular equation that involves a precipitate occurs right here. The net ionic equation is just this right here, where we remove the spectator ions and all the other things that are present. I think we will stop there and then continue on with the next section.